Yeah. And for those of you who didn't come today, can check your quiz later, maybe on Monday. Or for students who pass uh, the introduction class, maybe I will bring your quiz to the classroom so you can find your quiz on the classroom in the next course. Okay. Yeah, you can find. Oh, oh, you can bring it home. Yeah. For a quiz, you can bring home. You can find your quiz and you can bring home, and maybe you can check first before. How much you get? Yeah, it is really correct here. Yeah, maybe calculation. Okay, so please check your quiz. If there's nothing wrong, then you can bring home the quiz. Okay, and firstly, I I told you before on Monday class about our next quiz, but probably next quiz will be on first week January first week. So after New Year, so maybe on Monday. Yeah, yeah. We don't really have much time. So first week of January. So this will be quiz 6. Okay, quiz chapter 6 or quiz 4. And let me check. Okay, sorry, I'll accidentally left out. Sorry. Okay. Okay, so quiz chapter 6. Let me check the dates. Okay, New Year is Saturday, Sunday, Monday. Maybe January 7th? January 7th? Okay. Because I want to focus on finishing chapter 7 and having maybe a little bit review. Maybe I will give you additional video later on. So the topic will be chapter 6, include area, volume, and average value. Yeah, this is on Friday. Friday morning. Yeah, the choice is Monday or Friday. Monday, you are from holiday, right? You get holiday from Friday. 31st December, holiday, right? And then New Year, and then Sunday, Monday. I think better to get in Friday, so I can prepare finishing the chapter 7 and giving you maybe a little bit review, so we can have more preparations. Okay. And this will be the last quiz, okay, for our class, and we will have the final exam uh, maybe around 10 or maybe 12, okay, 10 to 12 in between those dates. I think that's the first information. Okay. Okay, next one. Maybe we can go to our feedback. Okay. Is the statement true or false? The statement is area between curves. Okay, sorry, is y equal f of x and y equal g of x for a less than equal x less than equal b is a equal integral from a to b f of x minus g of x dx. The answer is false because we need to know the statement whether f of x is greater than g of x or not. So that's why it's false. Okay. Okay. So yeah, we need to have this statement first to get to the formula. Okay. Okay. That is number one. Number two, we have area between all these curves. Okay. Y equals square root of x, y equal 1 over 3x from 0 to 16 of x. Okay. So if we try to draw or try maybe finding the intersection first, between these two curves. Okay. And we get that the intersection is on x equal 9. Okay, on x equal 9. We get the, if you want to make the equations, this is the equations. We have the intersection on 0 and 9. So the point on the middle is x equal 9, right? And because it's asking from 0 to 16, we will have two areas. Okay, so area 1 and area 2. And that's why we are going to have the first one is square root of x minus 1 over 3x. Okay. The other one is 1 over 3x minus square root of x. So this will be the equations for the area. So we have we'll have a1 and a2. So we need to a little bit calculations here and there. Plug in the endpoint 0, 9, and 16. We get that this is resulting 9. Okay. Okay. The important key point here is to know the intersection and which one the 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 curves. Okay, which one the curves. Okay, which one on the top, which one on the bottom. Okay. So the next one is uh, find the volume of the solid obtained by rotating the region bounded by the given curves and about the specified line. So this is the curves, okay, the boundary, and the x equal to is the center of rotation. Okay, so it's rotated about x equal to. Okay, now this is x equal to. I already draw. This is the y equal x cubed. Okay, this is x equal 1. And it should be this region is this. Okay, so this is the region. So you're supposed to rotate to x equal 2. So maybe I make it into a different color. Maybe this one. Okay. So this is the rectangle. If we want to use the this method or word washer method, so this will be the whole shapes looks like this. Okay. All right. Now what we need to find next is which one is the outer radius and which one is the inner radius. The outer radius is this one. Let me draw here. This is the outer radius. That's the outer radius, which is 2 minus x. X is a function of y. It's from the x cubed. So x is, or let me write here, that x is, so the radius will be 2 minus cubic root of y. Okay, that's the outer radius. The inner radius is exactly at the middle of 0 and 2, which is the x equal 1. So that is our inner radius. So that the calculations is, this is the inner radius. This is the outer radius. Okay. So we need to expand the quadratic first. Okay, Regina, wait for a moment. Okay. So let me. Okay. So we need to expand first, and then we integrate. This is the solution from 0 to 1. Okay, and then input 0 and 1 to the equations, we get the volume is 3/5 pi. Yeah, I think uh, yeah, I think if you get the inner radius and outer radius correct, if you are if you done this problem in exam, you will get at least already 60 to 65%, okay, or 55 to 65%. The rest is the process and the final results. Okay, so that's the number 3, question number 3. Okay, since they are asking about QR code, here is the QR code. Okay, if you haven't scanned, we'll give you 1 minute to scan. Okay, last time we have done our integration by parts, right? Okay, let me just review this first. Okay, okay. Okay, so let me review a little bit integration by parts. That the general formula we have u dv equal uv minus v du integral. And I gave you the another uh, another perspective, okay, on how the settings, okay, how to set up the integration by parts. Okay, so in terms of this integration here, u and dv, this is what we need to find or identify first before we try to calculate the integral. We need to define which one is u, which one is dv. Okay, and then we need to find the du, we need to find v. And after that, we need to set up our integral, become uv and v du. Okay, so this is where my method here that last time I told you came along. Okay. So di means that d is for the differentiate, so the element that needs to be differentiated, or in this case, this is our u. Okay, this is our dv, and actually, this is what it looks like. Okay, so what we did last time is we cross multiply from the left corner to the bottom right. Okay. We cross multiply that, and if the row, if this is not zero, this du is not zero, then we need to multiply the last one. But how to write this in terms of our equations? This uv, so plus multiply u multiply v. Okay, we write uv, and the bottom one here, the straight one, we need to write with integral. Okay, with integral. So we write with integral v du. Okay. So this is actually the same idea for the integration by parts. The difference is this is just a setup for a better calculation. Okay, easier to look at. Okay, compare with if you just look at the functions and maybe you take u and dv, you write down all the things, and probably you will get this. If the functions have derivable functions until maybe 5 times, then maybe you need to have like 4 times integration by parts actually. And to simplify that, we can having this settings. Okay, so the left one is the element that can be derived. The right one here, the I, the integral, is the one that need to be integrated. Okay. The idea is if the element, okay, like for example, last time we have x cubed sine x, okay, or sine 3x or whatever. This is just an example. If this is comes, then the left one here is better to be our derivative, and this one is our integral. Or this is u and this is dv. Okay. This is u dv. Okay. So we can write down this is x squared sine x. We integrate, we derive 2x become 2x, 2, and then 0. Okay, and sine x is going to be minus cos x minus sine x, and then it's going to be with multiply with the negative will be cos x, and we need to multiply all with this signs here. Okay, this how come this plus minus plus minus? This is coming from the uv minus. Uv have plus uv minus integral v du, right? So this comes from that. Okay. We can cross multiply here, and since the last row is 0, we don't need to calculate them, and we can directly get the answer without any integral left in the equations. Okay. Now, okay, what's happened if the last row is not 0? Then we can just do as the previous one. We can just write this and then just write the integral and maybe think another method to solve. Okay, if we cannot solve completely with integration by parts, so we need to think another solution. Okay? Like for example, last time we have the e to the x and sine x dx. Last time we already solved this, and if we look at both elements, e and sine, they are repeatable, either derive or integral, right? Either the differentiate, either integral. It will always be e, or sine, cos, sine, cos, sine, cos, and it can be really long, right? We are not stopping at some point. But when we integral or when we derive this, sometime in the middle, like we did before, we will find the original question, right? And then we can solve that. So same here. Okay? If we take this into our d and I method, okay? So this is u dv, and this is e x sine x, and this will be e x. This is minus cos x, and it's minus sine x. And up until here, we see that we have at least similar element with the original one. So we can stop here. Okay, we can stop at that point, and we can multiply this, and we can write in our equations. This is minus ex cos x plus ex sine x, and then minus with integral, and then we can solve as we have done before. We can solve by move the right part, the ex sine x, to the original equations, and we can solve the whole integral. And don't forget to still, you need to plus c, okay? You need to plus c at the very end at your results. Okay? Okay. I hope this method can help for at least if you see any repeatable integral, you can look up to this method. Okay, and actually, if maybe because sometimes other professor they look at this and they maybe feels that usually if you going to like a cram school or any tutorial, sometimes they give you like a shortcut. Oh, this is how it's done. Okay. But actually, if you are asking and how to put this in, how to prove this, you can go back to the original idea, which is this. Okay, this is simply a new setup from this integration by parts. We just move to our new table here. Okay. So if you are asked how to make sure that this is correct, you can go back to here. Okay, this integration by parts. Okay, uh, the other one, if you have the tangent inverse x. And this tangent inverse dx, um, if you look at and if you think directly, we don't have direct answers, right? We need to at least to get some approach with our integration by parts, at least. Okay. So the element will be the tangent inverse x and the x. Okay. And because tangent inverse x, we are not sure what's the integration of that, and this is the questions actually. So maybe we will put this into our u, okay, and the x will be dv, okay. So this is u, this is dv, or d and I, okay. So we can write this is tangent inverse x. We derive become 1 plus x squared. This is the x, and integral become x. And this is plus minus. We can just stop here just to see how it looks like. So this will be x tangent inverse x minus integral of x 1 plus x squared dx. Okay. And sometimes, okay, in your calculation, maybe you will see some functions that when you integral, it still has this another integral here that you need to solve with another method. Okay, then and that's okay. We can still solve this. And I think this is simple, right? The right one here, 1 plus x squared and then x. We can think of substitutions, just regular substitutions. Okay, so we can think this using the u sub. So if u is 1 plus x squared, and if you maybe confused on the variables, you can make different variable. Okay, maybe this is u dv, and maybe this is you can use z, or maybe y x, not x, maybe y, maybe w, any variable that you can think. So we can have this du the 2x dx, and dx is 1 over 2x du. So we can cancel x, and we will have 1 over u du, or we will have ln 1 plus x squared plus c. And the total solutions will be x tangent inverse x minus ln, or half, sorry, we have half here. ln 1 plus x squared over 2 plus c. Okay, aside from integration by parts, we will also have um, a trigonometric integrals. Okay, trigonometric integrals. Okay, let's start from, to begin with, let's start from secant squared x dx. We know that this is the tangent, right? The tangent. Okay, because we can also look at the tangent. We derive the tangent. It became the secant squared. Okay. Now the questions we will have is secant x. What is secant x dx? Right? And how to relate the secant x is, first is secant squared is it's a tangent. Okay, so we can think from tangent and secant. So let me go here and take the derivative of secant x. Okay, this will be secant x tangent x. Okay, and the second is derivative of tangent x, which is, this is the secant squared x. Okay, now from these two derivatives, okay, secant x and secant x tangent x and secant squared x, we see that these two results of derivative of secant x and tangent x, it has a same same or common element, which is the secant x. Okay, so this is just guessing and trial, right? Okay, so guessing and trial, what we will do with the secant x. Okay, so maybe, okay, if we look here, if you look these two, we can think something like, if we are multiplying these two, or we can take a factor from these two, we can take a factor secant x, that is secant x plus tangent x. Okay. We can multiply and see a factor. Okay. Okay. And because the secant x and tangent x will result the same as what we did here, okay, probably what we will do is we can multiply the secant x here with some elements. Okay, we can multiply with some elements. So let me write here secant x dx. Let's multiply with, or maybe the x, I will write the x at the end. So multiply with secant x plus tangent x over secant x plus tangent x. Okay, and of course I can't do this way, right? Secant x plus tangent x over secant x plus tangent x. That's okay. Why I need to multiply with this? Because I want to have our relations between the secant and the secant tangent x. Okay. Now, if we multiply, we will have a fraction that is secant squared x plus secant x tangent x over secant x plus tangent x, and then dx. Okay. By doing so, if we look at the secant x plus tangent x, okay, if we look at the secant x plus tangent x here, this is precisely, if you derive the bottom part here, if you look at this bottom equation, secant x, if you derive, it will be secant x tangent x, which is this one. If you derive this tangent x, it will be secant squared x, right? So why don't we use the secant x plus tangent x as our substitution, right? So we can sub the whole thing down there with u. And I can cancel the top equations, right? And so the equations will be 1 over u du. Or this will be ln u is secant x plus tangent x plus c. And this will be the results that we are expecting. And if you see any integral of secant x, you can answer directly. That will be ln and then secant x plus tangent x. And don't forget to have absolute value and plus c. Unless you know that the function is positive, you can ignore the absolute value. But just to remind you that maybe it's safer just taking the absolute value. Okay. Okay, this is one way to introduce to uh, trigonometric integral. Okay, I think if you look at the textbook, okay, look at the chapter 7, 7.2, trigonometric integrals. There are some summary conclusions, and you can try to read that out, but I think it's too many explanation. So I will try my best to make it short, but not that really short. Okay, so still you can see what is going on in this chapter 7.2. Okay, so 7.2, this is trigonometric integral. Okay, I call this case one. Okay, case one, we are going to look at our basic identity in trigonometry, which is sine squared plus cos squared equal 1. And basically, we will try to solve and look at this sine. So we will have some power here, m and n. Okay. And let me just give you an example on how we are going to solve this. Okay, rather than reading the words on your textbook, maybe it's too much words. Okay. So if we have sine with power of 5 and cos with a power of 2, okay, key point on how we can solve this, okay, is we are going to look at our basic identity, sine squared plus cos squared equal 1. So we can either take sine squared is equal 1 minus cos squared, or cos equal 1 minus sine squared. Okay. Now, if we look here, there is one power that is raising to the odd number, right? This is 5, this is 2. And by looking at the basic identity, we need to have at least 2 or even number, right? If you have 4, we can take it cos square and then square it again if we have 4. But if we have 5, what we will do is we need to separate one, and the rest will be signed with power of 4, right? Let's write first. Or let me just write directly. This is sine squared and then squared. Okay. Now the idea behind this trigonometric integrals is at the very end of the process, we need to substitute, okay, one of the elements in the integrations with use substitution. Okay. Just regular substitution. Okay. Now we will have this is having this sine x. Okay. And we know if we derive cos, it will result in negative sign. We'll derive sine, it will be cos, right? So if we look at the sine squared squared, this sine squared, we can change to 1 minus cos, right? 1 minus cos. So we can exchange this, become 1 minus cos squared x, and then squared, and then cos squared x, and then sine x. And the idea here is we need to cancel this sine x here. So I think it's already obvious that we need to substitute this cos. Okay? So that's actually the idea behind most of trigonometric integrals. Okay. So we let the u is cos x, that our du is negative sine x dx. Okay. So we will have a negative. This will be 1 minus u squared squared and u squared, and then du. And we need to have some calculations first before we integrate the whole thing. So this will be 1 minus 2u squared plus u4, and this is u squared. So this will be u squared minus 2u4 plus u6 du. So negative, I will write the answer directly, 1 over 3, and u is cos, so cos cube x minus 2 over 5, cos with power of 5x, plus 1 over 7, cos with power of 7, x plus, oh, sorry, this is plus, this is minus. Okay, that's the idea. So whenever you find like, if you have sine squared x cos 5x, okay, for example, this one, what you need to do is you can look the power, and you need to make this in this form so that this one this cos squared will be 1 minus sine squared, right? So you can use u is sine x to remove the cos, and I think you can do it by yourself here. Okay. It's a similar key concept with the previous one. Okay. So we'll have sine and cos. Okay, the first case, sine and cos. And we will move to second case. Okay, second case, case 2. So let me write again this basic identity equal 1. And whenever you forget the other terms, we can multiply this with 1 over cos squared x, right? And then we have tangent squared x plus 1 is equal secant squared x. Okay. Now this will be our case 2. Okay. Tangent and secant. Also, to write down the first, okay, we need to write down the secant x tangent x as we did before. What is the derivative? Okay, and this will be our considerations in the substitutions. This will be secant x tangent x. This will be secant squared x. Okay. Okay, so if we have an integral and we have a tangent and secant inside with some power, for example, tangent 5x and then secant 7x. Okay. If we look at the idea behind the basic identity, the tangent squared x plus 1 is a secant squared x, then if we look here, this is 5. If we are not really, it's not really clear. It's 5. So tangent with power of 5x, secant with power of 7x. We have 5 and 7. So what we can do at least, maybe we need to try to reduce this, become 4 and 6. And then we will have a secant tangent separate. Okay, so this is tangent 4, secant 6, and then secant tangent. Okay, probably. Okay, so let's try that way. So this will be tangent 4x and then secant 6x, and then we have secant x, tangent x, separate from the original equation. Now, the idea behind this case 2 is basically what we need to substitute at the end is secant tangent or the secant square. Okay, what we need to substitute. Okay, not secant tangent. I mean secant and tangent because their derivative we can cancel and we can cancel because of the substitution. Okay, so with these equations here, if you want to get the secant tangent, we need to substitute the secant. Okay, so we need to change the tangent to secant. So let's try to doing that. This tangent 4 is tangent squared x squared. Okay, or this will be secant squared x minus 1. And this is secant 6x. This is secant x tangent x dx. So we can substitute u with a secant x because du is precisely secant x, tangent x, which we can cancel this. So we will have, u squared minus 1 squared and u6 du. Again, we need to solve this first. Okay, then we can try to write down. This will be a secant 11x minus 2 over 9 secant 9x plus 1 over 7 secant 7x plus c. Okay. Okay. Do you need 5 minute break? No. Need. Okay. 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 5 minute break. QR code from the top one. Okay. From maybe from here or from here. I think too small, right? Maybe here first. At least the whole the case too. Hey, you already have the schedule for final exam, like maybe chemistry or maybe physics. Not yet. Chemistry lab, you need to go to take the writing or writing final exam. Yeah. Okay. Oh, anyway, some of you need to have the next semester. Some of you conflict with the material science, or right, right. Yeah. Uh, you can get the my code for the other class, but I think I can give you later because I think the system now cannot give me the code. So maybe later. The system is still not confirming the code. Okay. So maybe waiting for the next semester. Okay. So I think that's okay. I will still give. Okay. Maybe later I will give you maybe like a Google form to fill in. Okay. At least I want to know how many the numbers. Okay, let's go back to, okay, okay. The first one, if we have this tangent with power 5 and secant with power 7, the second example is, let me write the second example here, is if we have both tangent and secant in an even power. So maybe tangent 6x or secant 4x dx. Now, if you have this, then to get the u substitutions, then we need to separate the secant squared. Okay. So if we look here, we can write secant squared like this. Okay. So you can check the power. If tangents and secant have the same power, odd power or even power, then you can use the trigonometric integrals. Okay. And by doing this, we can take the u as tangent. So we can have tangent 6x, and then the secant squared x, it will be tangent squared x plus 1, and then secant squared x dx. And we can substitute a tangent. And it was completely cancel the secant squared x. Okay. So you can solve this, and I believe similar with the previous one. Okay. But the key important here is the tangent secant, they need to have, a, if not odd power, the same odd or even. Okay. So 5, 7, 6, 4, or 3, 5, 4, 6, 4, 8, and so on and so forth. Okay. If they have maybe even and odd at the same time, maybe that will be the difficulty. Okay, so that's the trigonometric integrals. Okay, the next section, okay, so that's the 7.2. The next sections will be the trigonometric substitutions. Okay, it's a little bit different. Because in these trigonometric substitutions, what we need to substitute is the variable with the trigonometric function. Okay. Okay, let me write our two basic identity in trigonometry. Okay. So from these two equations, we can get that the sine squared x is 1 minus cos squared x. Cos squared x is 1 minus sine squared x. And from here, we get, aside from that, is tangent squared x is secant squared x minus 1. Okay. So at least we have this equations. Now, the idea behind the trigonometric substitutions is, let me just give you what this looks like, okay? How we can use this method. The first is, let me give you the, okay, maybe x squared, and then this also x squared minus 9, and then dx. Okay. If you look at this integral, if you try to take it into integration by parts, Not sure if it is okay or not. If we take the substitutions using usub, I don't think we can substitute easily, right? Now, what we can do is we can substitute, but with trigonometric approach or trigonometric functions. If you look here, this is having x squared minus 9 in the under the square root, right? So it's a variable minus a constant. Now, if we look at the trigonometric functions and identity that we have, we will have at least this one, right? The secant. So probably if we try to substitute the variables with a secant functions, maybe we will get these terms, and we will get, if we are going to take this, we will get the tangent. And it usually it's under the square root, and we can remove the square. Okay. So that's how usually the method works. Okay. So if we look here, the constant is 9. Okay. To make out the same 9 as in the trigonometric functions, then we can take the x as 3 secant. Let's write a theta. Okay, let's write a theta, another variable to substitute. Because if we write down the squared, we will get this result. And this is 9 tangent, right? Okay. And don't forget to also exchange the dx. Okay. You have to also exchange the dx. The x is, we need to derive this, become 3 secant theta tangent theta d theta. And we need to exchange the whole thing with the dx. Okay, the whole thing with the dx. Okay, now we can write integral x squared is 3 secant theta squared, so it's 9 secant squared theta. Okay, and this bottom here is our 9 tangent squared theta, or we can directly write, because it's square root, it's become 3 tangent theta. Now the x become, let me write at the top, 3 secant theta tangent theta d theta. Now this is become a new integration, and we can try to solve first. Okay, we can try simplify 3 tangent secant secant. So we have this 1 over 9. 1 over secant is cos theta, right? And the integrations of cos is sine. So we have sine theta. Okay, but it is on theta. Okay, it should be a plus c here, but let me just finish this. Because it's still in theta, we need to go back and revert the integrations, or revert the results into the variable x. Okay, we need to go back to x. Okay, so first we need to take this as our definitions of x, because we did define this x as equal 3 secant theta. So we can try to draw the triangle. Draw the theta here. Okay. And x over 3 is secant theta, right? From our definitions. So cos theta, if you maybe have confusion here, is 3 over x, right? So 3 here, x there. And the one at the opposite side is x squared minus 9. Okay. Now the question is sine theta. We need to have the sine theta. So sine theta is x. The sine theta here is squared of x squared minus 9 over x. So that is our answer. So 1 over 9 x squared minus 9 over x plus c. Okay, so you will know when to use this method when you see usually you will have the square root and something squared inside, minus or plus, okay, minus or plus. The variable and the constant, usually that will be the case, okay, for this trigonometric substitution. Okay. So you need to at least preparing some strategy to solve the integral. Okay. My idea or my suggestions, you can think first the simplest way is substitution. Next one is the integration by parts, and the other one is maybe you can think trigonometric integrals or trigonometric substitution. Or even if you can think like using the guessing method, you can think what functions that when you derive it will become the integral. You can also use that way, and sometimes the guessing will be very fast if you can think faster. Okay. But if not, then we can try to substitute or integration by parts or using this trigonometric. Okay. Okay, so this will be the case one. Okay. Case two. Okay, case two is if you have a constant minus a variable. So if we look at the function, our trigonometric functions here, a constant minus variable, we can have at least this a or b, right? So we can have sine or cosine. If you let the x become 3 sine, okay, so we will have 9 minus 9 sine squared theta. This will be the whole thing will be 9 cos squared theta, or this will be 3 cos theta, and you can have this, okay, and our dx become 3 cos theta d theta. Okay, now let's try to substitute the 3 with power of 3 sine cube theta, and then we have 3 cos theta and 3 cos theta, so it will be 3 with power of 2 cos squared theta d theta. This is 3 with power of 5 sine cube theta and cos squared theta d theta. And this will resulting in our early introductions of trigonometric integrals of sine and cos, right? So we can take this approach. We can substitute with cos. So substitute with cos. So we will have a negative. Okay. You can have this as u squared minus u4 with the negative, right? let me change the positive at the front, so the whole thing becomes 3, 5. I will exchange this u4 and u squared u and integrate. Sorry, u4 becomes 1 over 5. U is cos theta and minus the and again we need to know our definitions of our x and theta. Okay, we will have this is theta, so x over 3 is sine theta, so this will be x, this will be 3, right, and this will be 9 over 9 minus x squared. And we need to have cos. So cos theta is, I need to exchange all of that. So this will be 3 power of 5 square root of 9 minus x squared. So this will be equal to this, right? So we need to have oh, this is 3, sorry. Yeah, and you can try to solve this. Cancel, and also become 3. So and this will be 1 over 5. Yeah, that will be our answer. And actually, you can also try to use the x equal 3 cos theta. Not sure if the answer is the same or different, but if it's different, that's still okay. That's why we have the constant, the plus c. That will be the differences. Okay? Yeah, in integral, don't forget to write the plus c. Okay, some of you forgot to wrote down the plus c. Okay, maybe any question first? Okay, if not, then let me continue. One more case. So the case 1, case 2, and the last one is the case 3. Case 3 is you have okay, and on case 3 you have a variable plus. You have plus a constant. Okay, let me remind you that this is about the tangent squared x plus 1 equals secant squared x. So this is using a tangent. Using a tangent. So if we let our x equal 3 tangent theta, so we will have this 9 tangent squared theta plus 9, or equal with this 9 secant squared theta. Okay. And if we derive, this will be 3 secant squared theta d theta. Okay. Now if we substitute all x with the 3 tangent theta, this will be 3 cube tangent cube theta. This will be square root of 9 secant squared, 3 secant theta, and dx will be 3 secant squared theta d theta. This will be canceling. So we will have 27 tangent cube theta secant theta d theta. And this is also similar with our secant tangent forms, okay, from the previous sections, right? Okay, now we see that this is tangent cube and a secant with 1 power, so it's odd. So we can separate tangent and secant, okay, and we have tangent squared. Okay, so we will have and we can take this and we can let another u take our secant. So this will be 27 u squared minus u du. Then we will have 27 1 over 3 secant squared theta minus u is secant theta. It should be plus c here. But again, we are going to look at how uh, how it performs in a triangle. So x over 3 is equal to tangent theta. This is x over 3, like that. And the hypotenuse will be x squared plus 9, like that. So the secant, or maybe start from the cos. Cos theta is 3. So the secant will be, okay. Now this will be resulting 1 over 3. The secant squared is x squared plus 9 over 9 minus x squared plus 9 over 3, and then plus c. We can cancel some parts of this. So x squared plus 9 Oh, should be 3. So it should be 3 over 2. So x squared. So this should be 27. So 27 should be having 3 at the bottom. So 3 over 2 minus secant theta. Oh, wait. This will be u squared minus 1. Should be 9, right? And plus c. Okay, so that's the third case. Okay. So you need to look at the pattern. First is having the some x squared minus a constant, right? Uh, a constant, maybe a minus a variable x squared, and then x squared plus c, and usually it's going to have this square root. Okay, this we will have a secant theta, and this will be having a sine theta or cos theta, and this will be having a tangent theta. And I think that's it for this is 7.3. This is 7.3. The trigonometric substitution. Okay, the next sections is I already mentioned before at the maybe a few weeks ago. I think I already mentioned. It's called the partial fractions. Partial fractions. Okay. Okay. What's partial fractions? Okay. So this is a method to separate a big fraction into several fractions. Okay. For example, okay, let's start with um, this. Okay, let's start with this one. If you want to combine these two fractions, then we can simply multiply the bottom, right? And then the bottom, this whole composite, we divide with each of the denominator and multiply with 2 and 1, right? So this will be resulting 2, multiply with x plus 2. Okay, minus is going to have x minus 1, like that. Okay, and we can compute this. This will be 2x plus 4 minus x plus 1. This will be x plus 5. And the bottom one will be, we can compute this, x squared minus x plus 2x plus x minus 2. Okay. Now, the idea here for partial fractions, if we have integral of x plus 5, x squared plus x minus 2 dx. Okay. Okay. Usually, what partial fractions will do is, if we have this, and we are not sure how this is will be in terms of the technique of integral, what we can do here, if we see a big fraction like this, probably what we can solve is at least we can separate this part becomes this two. Okay? And that way will be more feasible to be integrated. So if we can separate it become 2, this way we can have 2 ln x minus 1, right? And then minus ln x plus 2 and plus c. It's a better way to solve, right? To separate. Okay. So the general forms or the general idea is if you have a function that is a fraction, let's say p over q, and p and q is a polynomial, okay, both are polynomials, and if the degree or the power p degree is greater than q, like we have in usually in chapter 4, finding the slant asymptote, right? If you remember, uh, we can use the long divisions. Okay, use the long divisions. For example, if the f of x is x cubed plus x divided by x minus 1, we can use long division, or even at this case we can use the syntactic one. But I think let me just stick with the long division here. Okay, this will be started with the x squared. So it will be 2x plus 2, uh, 2x minus 2, and we will have this will be 2. So the whole functions become x squared plus x plus 2 plus 2 over x minus 1. And if we want to integrate, this can be one solution. Okay? And you can integrate this easily. That's one way. Okay, one way to solve. Okay. That is if the p is the degree is greater than the q. So first, long divisions. Another method is actually the first example that I show you here. Okay. the partial fraction. Okay? So if you look at, okay, if f of x is p over q, if q is factorable, then of course you can factor q. So we can express as a sum of partial, which means this is, we can factor as a, write down the sum as ax plus b with some power I, or ax plus b, and this will be ax squared plus bx plus c with power I. Okay, I think I can go example one. Okay, maybe just until this one, and then we can finish the course. Okay, if we have this, first look at the denominator, the q. If we can factor it, let's try to factor. So let's try to factor x first. Okay, that will be our factor, and I think we can try to factor that out. So we have 2x squared, 3x minus 2. This is my suggestions to factor. So take a table, take sometimes to try some number. 2x, it will have 1, 2, should be negative 1 here, 2, yeah. So we will have x and 2x minus 1 and x plus 2. Okay, and then what next? The next thing is, let me write in a new equations just the fraction. We can write into 3 terms. The first one is over x plus over 2x minus 1 plus x plus 2. This will given a constant a, b, c as mentioned. Now, our goal is to find a, b, c. Okay. So first, we can think this all fractions here, like we can combine together, and we can have equations up there. Okay? So let me finish this a little while. So this will be a 2x minus 1, x plus 2, plus b, x plus 2, x and x plus 2, plus c x and 2x minus 1. And we need to equal this with x squared plus 2x minus 1. Okay. So we need to solve this first. Okay. Group each x squared, x, and a constant, and then solve the system equation, the linear equations. Okay. So this will be x squared plus x and then plus a constant here. Okay, let me continue this part later on Monday. So we will continue this part and still have some definition on partial fraction, and we can move on to the other sections as well for Monday. So again, quiz will be on January, okay, first week of January. So before we end our course, as usual, I have feedback questions, okay, for you. But before that, is there any question? Any question? No? Okay. We can start the feedback. Let me stop this. Okay, this is to check the our volume and the integration by parts. Okay. I hope I hope that's okay. I just want to know if you guys can still get the concept, okay? Or at least get to know how to calculate the volume. Okay. How many? only, and only in the classroom. Okay, that's okay. Oh, okay. There's one more. Okay, okay. Okay. Anyway, I think we can start. Oh, nine people. Okay, 9 people. Okay, let's start. 3, 2, 1. Okay. Yeah, you need to write in fraction. You write in fraction. The smallest fraction. Okay. So you have a y, some function of y and then squared, maybe like this, right? And some x equal 4, and rotate about y equal 1. Mm. Okay. Okay. You need to use the shell method. If you use the disk, we will we will get confused. Okay. 45 seconds. You give up? Okay, okay. That's okay. That's okay. Okay, 7, 6, 4, 3. Oh, yeah, there's one student get correct answer. Okay, go, go, go. Okay, one student. Okay, one student got correct. Okay, one more question before we close the class. Okay, 3, 2, 1, start. Okay. At least I give you options to choose. Very good. Good. Okay, around 2 minutes, 50 seconds. You're making more difficult here. Yeah, yeah, yeah. No, no. It's wrong. It's integral. No, wrong, wrong. Yeah, yeah. You can check. Try to derive. Can it be here? If you derive, don't forget the chain rule. Right, right. Okay, around 1 minute. Okay, 40 seconds. You got it? No? Okay. Okay, yeah. Congratulations. Okay, that's really the end of our course. Okay. So see you next Monday. Okay.